So I'm going to record on the computer. Right now we're recording, folks. So we're going to start our lesson here. In order to start our lesson, let me just delete the stuff that's here on the board. All right, and oops. Okay, that takes a little bit of time to take care of it. All right, so I'm going to start writing over here. So our first lesson, folks, is going to be 4 ways to represent a function. So I'm looking at the book here. So lesson 1.1, 4 ways to represent a function. Now, if somebody asked you about a function and says, what do you mean by a function? So what's a function here? In college algebra or college algebra intrigue, you learned a bunch of abstract definitions. And, I agree with those. They're useful, but not particularly useful in this context here. So let's kind of talk functions in plain English so everybody can understand what a function is. So, folks, a function is in math generally is a procedure, not only in math, in some other subjects as well, like computer science and such. So it's a procedure that takes an input, something here. So this is an input here. There's going to be some sort of process, which is a black box if you want. And then there's going to be something else here. So this is going to be an output here. So for example, an example of a function is a function of many variables. If you want, we'll discuss about variables a little later. So we'll only do one function, functions of one variable. But this is a good example to keep in mind. So let's say the process of making a soup, for example. So when you make a soup, what you do, you put the ingredients here. So what do you need for a soup? You need salt, you need, vegetable stock, and you need some other things there. So that's the input here. The process of cooking is mixing those and boiling and doing stuff. And then at the end of the day, you come out with the output, which is your soup. So your soup is the output here. So that is a function. All right, so now with a function, however, this is not very helpful here in calculus, because in calculus, we all talk about functions as some sort of formulas. Now, is there truth to that? Yes, there is truth to that, because a function, folks, most likely in calculus, what you'll see things like this. So people casually say, how about this? F of x equals x squared plus 1. So we all know that this is a function, but why is that something that follows this process that was designed here? Well, that's because, folks, this is an input-output situation. So x is the input, which could be a number, right? A number like x could be 1, could be 0, could be 7, could be 0.3, or something like that. And then the output is going to be the result of this calculation, where you square x and then you add 1. So the output, for example, when you input 1 here, the output will be 1 squared plus 1, or 2. When you input 0, the output will be 1, and so on. So for each of these, you will have an output, and it's given by this particular formula. These are the types of functions that we will study in calculus. Now, you might say, oh, I already knew these things, so why would I have to worry about that? Well, you have to worry about that here, and why do I have to review that? I'm assuming that most of you, or probably all of you, know about this thing. But the thing in calculus is sometimes we aren't able to quite get a formula. So what we do here, when we have a formula here, that's that's one of the 4 ways to represent the function. And they tell us here in the book that the first way to represent a function is is by using a verbal description. So let me just switch. Let me just change pages here. So there's four ways to represent a function. So the first way to represent a function is by a verbal description. All right. And to represent a function by verbal description, I'm going to say, for example, here's an example of a function. So if I go to the store, which I don't go nowadays because they're all online, but if I want to buy a pair of shoes and I look at the shoe rack over there, I can see a price associated to each pair of shoes. So that is a verbal description, and I could say that that the pair that looks brownish has a cost of I don't know $45 or something like that. So that is a verbal description of a function. Now functions can be described verbally in many ways. We can describe a function such as the length of a segment or the area of a square or something like that. Those are functions that are described verbally. So they're not given by a formula, but our goal is to create a formula for those functions. So it's important to understand, and especially in practice, if you want to become an engineer or something like that, every time you solve an engineering problem or a math problem for that matter, you are going to appeal to this verbal description first. So you are going to say, I want the forces at a certain point to balance each other so that the construction doesn't collapse or something like that. And that's the first description of a problem. It's a verbal description. And then if you want to define a function there, then you have to define, a function in terms of whatever variables you have there entering the problem. All right. So most functions, however, in math, in calculus, will not be described verbally. Because in calculus, we are going to focus on more like formulas and stuff like that. So what other options are there? Well, the next option here is, they say, describe a function numerically. So there's a numerical description of a function. How does that work? Well, a numerical description of a function very often appears or happens in, let's say, the medical field. If I want to measure a patient's heartbeat, right? So what I'm going to say at time t equals 1, after 1 second, I measure the heartbeat and I notice that it is, I don't know, 72 beats per second. And then I measure after 3 seconds, and then I notice that the heartbeat is 78 beats per second. And so on. So that basically describes a bunch of measurements at various times, or the heart blood pressure, or the blood pressure, or whatever. So that describes a function. However, I don't know a formula for this particular function. So you see, I don't quite have that possibility of saying, oh, the formula will be this, because if I knew a formula, then I would not need to measure anything. I would just stay home and I could tell you that your heartbeat is 100 beats per second. So we don't have a formula. So we can use this description, but this description is not perfect. So one ideally would like to derive a formula. When is this numerical description useful to, and when is it desirable to derive a formula? Well, ideally, every time you have a problem, you should be able to derive a formula, but sometimes it's not possible. So I'll give you an example when it's not quite possible. Even though we would like to have a formula, for example, if we measure the stocks in the stock market in one day. Well, you will hear that the stock price for I don't know, the 3M stock, right? A local company here is, I don't know what it is, but let's say is $100 per share. But that's today. But tomorrow, so stock values. Today, $100 per share. Tomorrow is, I don't know, 110, 105 per share. And so on and so forth. Ideally, we should get a formula predicting the stock values, but you know that that's not possible, because if anybody knew a formula, then they would get rich very quickly. So, there's approximations, there's estimates and things like that, but that's not a formula, a true formula. All right, so that's where we use the numerical description. However, that is not, again, is not a lot useful in math, because we would want to get a formula. So what else do we have there? Well, we would have a visual description. So, so the third way to represent a function is by visual description. In other words, by making a graph. Now, I don't know if the Corona dashboard is still up on our school's website, but that would be a visual description. So it would be measuring the number of infected students every, I don't know, every day or whatever they do there, every week or so. So that is a graph. Is that useful? That's very useful, because based on that graph, or the stock market too would be a good example. So, so let's say if you look at the, since we talked about the virus, so if you look at the infection rate, it was very low at the beginning, and it was spiked up, and it went down for a while, and it goes up again and goes down, and things like that. So, so hopefully by the end of the semester, it's all down. But this is a visual description, folks. It's by using a graph. Is that useful? That's very useful. Why? Because we can compare the value at various points. So let's say this would be, I don't know, September 1st. And if you compare, oh, we can see that just by looking at the visual description, there's more numbers than it was on, I don't know, on July 1st or something like that. So, so just by looking at the visual description, you don't need to know what the numbers are, but just by comparing those segments, which one is higher and which one is lower, you can still say something about the graph. This is very important. Again, we don't necessarily know a formula. Of course, this visual description is based on some numerical data, but what's important here is that we can kind of say something about the graph. Well, it's increasing or decreasing or things like that. Pieces of information that are still useful to characterize the particular function. And finally, the one that's most useful for us is the algebraic description. And this is the one that I always talked about. So algebraic description by a formula. And I would say that this is ideal. So it's ideal because in practice, as we discussed earlier in this class, we are not always able to give an algebraic description, and therefore we have to use some very specialized tools to study functions for which we don't know an algebraic description. However, in this class, in Calculus 1, and this is where I'm kind of wrapping up the lesson, in this class, we will mostly focus on functions that are given by this algebraic description. So we will always have a formula. It's either something like f of x equals x squared or f of x equals sine x. We're going to review trigonometric functions when we get to that, or some other type of function. So we'll always have a formula, folks. In the rare situations when we don't have formulas, you will see that we'll have to kind of specialize our discussion to address those situations. So this is essentially all I had to say about this particular lesson. You can read in the book, they discuss about the vertical line test. So when a function is given, you know that when you draw a vertical line, you intercept the graph at exactly 1 point. And there's a bunch of other examples there where functions, the examples of functions given either by formulas or piecewise defined function by formulas on various intervals and stuff like that. So I am not going to address those. But what I'll say here before I close the lesson is that in this class, I strongly recommend that you go to www.desmos.com. And this is going to be a site that we are going to use very often to test our formulas and to draw graphs. So I'm going to, so you are expected to know some basic graphs like the linear functions and things like that. And we're going to review those as we get to them. But everybody should be able to, and I am going to share a screen with you here in a second. So, so let me share a screen with you over here, and I'll show you where that Desmos is. So desmos.com, this is free. There is an app if you want to download an app for your phones. Let's see, resources. So where is the app? There's an app here somewhere on the page. No, I don't see the apps here. So so kind of try to look on the page. I'll find the app next time. But for me, folks, for me here, the important thing is to go here to this page. And again, if I want to graph a function, I'll say very quickly f of x equals, and I'll say, let's say I do x squared plus 1, x squared plus 1. I type x squared plus 1. And there we go, voila, my function is graphed here. So we will do a bunch of experiments using Desmos in this class just to visualize, again, that visual aspect, the number 2 part of my lesson, right? Visual description of a function. That visual aspect is very important in understanding calculus. All right, folks. So this is the end of the lecture today. Do you have any questions for me before we close the recording here? So I'm actually going to close the recording. If you have any questions for me, how do I do that? 1 second.